first of all, what is a dimension? How many dimensions are there? And how do we know? How do we know that we're in 3 dimensions precisely?
Sure. So, um, okay, what is a dimension? So a dimension you can think of as like um, kind of an axis where you are free to move along, right? So when we talk about x, y, z, x is a dimension where you can define as forward, backwards, for example.
Right.
Y this way, z up and down. Those are the 3 spatial dimensions. There are 3 spatial dimensions as far as we know. Well, yes, there are, because we experience our lives in 3D. Um, but people do talk about like extra dimensions being out there, extra spatial dimensions. Of course, they can't be too large, because if they were large, then weird things would happen. Like things could just disappear. Like you can imagine a situation where like, if I lived in a 2D world, but there was um, if we were in 2D and I did this,
Yeah.
the pen from your perspective is just completely gone. It just disappears. But because we're in 3D, you know that there's something behind.
You might want to turn it for the camera, actually.
Sure.
Yeah,
Okay. I take the pen, I move it this way.
it disappears.
It disappears. But you know in your head, because there's a third dimension, that it's actually just behind us.
Right.
So in sort of subatomic physics, you can do the same, play the same game. You have a particle, does it disappear? Is there energy missing from some interaction? And that energy you can think of on a very high level as like leaking into these extra dimensions. So as far as we know right now, this doesn't happen. We search for extra dimensions and we don't see them. But that doesn't necessarily mean that there aren't any. It just means that they are not large, in the sense that as far, like X, Y, Z, we can move a lot in each direction,
Yeah.
right? But maybe there is an extra spatial dimension that's just so tightly curled up that things that are larger than that size can't actually enter them. So you can imagine like taking a piece of paper. This is large, but now I roll it up really, really tightly. And now my coffee cup doesn't really experience this dimension anymore. It can't like be inside it.
But what you're saying is that it won't interact with that curled up dimension. It'll still interact into the 3D.
Yeah.
Okay.
So it seems like in our world, this is how things are, but it's not saying that there are extra dimensions. It's just if they are, they have to be smaller than some scale.
Interesting.
And there's also other like constraints you can place on these things.
Okay.
Yeah. This is also not my area of expertise.
Yeah, of course. And do we know how many? What's like the theoretical limit to these extra dimensions?
No, well, yes, people know. I don't know off the top of my head. But I think it's still, they're talking about it on very small scales, like sub-micron for sure, I think.
What is that
Like
measurement?
1 micrometer is like 1/1000th of a millimeter.
Okay,
a
so 10
million
to the
times,
minus 6.
Yeah, a million times smaller than a meter.
Okay.
Yeah, exactly.
And that's where the extra dimensions might lie.
No, it's just saying that this is like currently, I think, the limit, but it might be way smaller than that.
Okay.
So of the size scale of the extra dimensions. It's not where they might lie, but it's like how, It also changes a lot about other physics. So, if you have gravity, for example, being this kind of not fictitious, but like not a real force in the sense of it's apparent as a force, but it's not really something that's an interaction. If you have extra spatial dimensions, it changes how gravity would behave on those scales. So I think there are people out there in the world who are trying to measure gravity at very short distance scales and try to search for these things. I'm not one of those people.
No, you're not. And so there's this other thing that you talk about, which is I'm probably going to butcher this, and feel free to correct me, is the isotropic 1/r², and that's how we know we're living in the 3rd dimension. Could you go a bit more deeply on that? Because I found that to be very, very fascinating, that there's like a direct proof of 3 dimensions.
It's not a direct proof. It's just like, so logically, if you work out like, you have something that's being emitted isotropically. So just for context, isotropic just means everywhere equally. So if I have a point in space and it emits like a something hot and it's very, very small, it would emit light, in this case infrared photons, isotropically in a sphere, right? So if you imagine the sphere and you have a little sensor somewhere on the sphere, the number of photons hitting your sensor would change depending on if you're really close or very far, just because of the effects of like things spreading out, right? So you can imagine this as like, what is the surface area of the sphere? It's 4 pi r squared. So forget the 4 pi, it's just a constant factor.
Right.
You have this r squared term. If we move further and further back, that means as a function of the radius, the distance from the source, you drop off in intensity as 1 over r squared. Okay, so as I'm really close to the source, more photons are hitting my sensor, and my eyes in this case. As I'm really far away, less photons are hitting my eyes. And that scaling factor would be r squared, or 1 over r squared. This is the inverse square law.
Oh yeah.
The reason it's related to this three-dimensional thing, the fact that we live in a 3D space, is because you can imagine a sphere in 3D has this surface area of 4 pi r squared. But if you add extra dimensions, the surface area of some geometric object like that, that is getting larger, doesn't scale as r squared anymore. So that's how we know, like on a kind of everyday basis, that we have 3 spatial dimensions. That's not how we know. I mean, you can also just walk forwards, backwards, and jump up and down.
Right. But that's not a formula, right?
What do you mean it's not a formula?
Like walking forwards and backwards is not a formula.
Sure, yeah. But you can do measurements of intensity falling away as a function of distance. And
Okay.